Supervised learning involves training a model on labeled data, where the algorithm learns to predict outcomes based on input-output pairs. In contrast, unsupervised learning deals with unlabeled data, identifying patterns or groupings without predefined categories. Both approaches are crucial for tasks like classification, regression, and clustering, each offering unique insights and applications in data analysis.
Machine learning is a transformative technology reshaping problem-solving across fields. It powers recommendation systems, enables diagnostic tools, drives autonomous vehicles, and supports language models. Its widespread adoption is evident, yet understanding remains limited. This scene explores its integration in daily life and advanced technologies, highlighting its significance as a 21st century advancement. Machine learning has revolutionized problem-solving, becoming a pivotal advancement of the 21st century. It's integral to recommendation systems, healthcare diagnostics, autonomous vehicles, and language models. Despite its widespread adoption, understanding remains limited, highlighting its transformative role in reshaping technology and daily life. Machine learning represents a paradigm shift in programming, moving beyond explicit coding to learning from data. It addresses traditional programming's limitations by identifying patterns and adapting to new scenarios. This approach handles real-world complexity, offering scalable solutions for intricate tasks, and expands the range of problems computers can solve, tackling challenges once deemed too difficult. Machine learning's foundational concepts are crucial for understanding modern artificial intelligence. Supervised learning uses labeled data to train models for tasks with known outcomes, while unsupervised learning identifies patterns in unlabeled data. Grasping these paradigms is essential as they differ significantly in their approach to data learning, impacting artificial intelligence's application and effectiveness. Traditional programming involves writing explicit rules for each scenario, effective for predictable tasks like spam filters. However, it struggles with complex tasks, such as image recognition, due to the combinatorial explosion of scenarios. This limitation highlights the need for alternative methods, as rule-based systems become impractical for nuanced problems. In the machine learning paradigm, computers learn from examples rather than explicit rules. Unlike traditional programming, where humans specify both data and logic, machine learning systems discover patterns from data. Arthur Samuel defined this in 1959, highlighting that systems improve through experience, not direct instructions, allowing them to infer logic autonomously. Machine learning involves tasks like email classification, stock prediction, and face recognition. Experience is gained from data such as labeled emails, historical prices, and photos. Performance is evaluated using metrics like accuracy, prediction error, and precision. As systems gain more experience, their performance on these tasks improves, aligning with the modern technical definition of machine learning. The machine learning process begins with data collection, ensuring data is relevant and high quality. Models are selected based on the problem, using structures like linear models or neural networks. Training involves adjusting parameters with algorithms to learn patterns. Evaluation tests the model's generalization on new data, followed by deployment and monitoring for performance. Machine learning is categorized into supervised, unsupervised, and reinforcement learning. Supervised learning uses labeled data to map inputs to outputs. Unsupervised learning identifies patterns without labels, while reinforcement learning learns by interacting with environments. Hybrid approaches combine these methods for practical applications. Supervised learning involves a supervisor guiding the learning process with labeled data. The goal is to discover a function that maps inputs to outputs, enabling predictions for new inputs. Training examples consist of input-output pairs, helping uncover underlying relationships. Mathematically, inputs are X and outputs are Y, forming the basis of the learning process. Supervised learning problems are categorized into classification and regression. Classification predicts discrete categories, such as spam detection or medical diagnosis, with binary, multi-class, or multi-label types. Regression predicts continuous values like house prices or stock prices. The key distinction lies in output type. Classification yields categories, while regression provides numerical predictions. In supervised learning, each dataset example comprises an input feature vector and a correct output label. Features like square footage or pixel values are crucial for tasks like house price prediction or image classification. The training algorithm adjusts model parameters to minimize prediction errors using loss functions, such as mean squared error, and optimization algorithms like gradient descent for iterative improvement. Model complexity poses challenges. Simple models may underfit, missing true patterns, while complex models risk overfitting, capturing noise. Overfitting leads to models excelling on training data, but failing on new data, as they memorize rather than generalize. Techniques like train-test split, cross-validation, regularization, early stopping, and data augmentation help mitigate overfitting, ensuring robust model performance. Supervised learning algorithms include linear and logistic regression, which model relationships as linear combinations of features, serving as effective baselines. Decision trees partition input space with hierarchical rules, offering interpretability, but risk overfitting. Random forests, ensembles of decision trees, reduce overfitting and enhance performance. Support vector machines, neural networks, and k-nearest neighbors further diversify the toolkit. Supervised learning revolutionizes healthcare by diagnosing diseases from medical images, predicting patient outcomes, and identifying high-risk patients. In finance, it enhances credit scoring, fraud detection, and algorithmic trading. Natural language processing benefits from sentiment analysis and text classification, while computer vision and recommendation systems also see significant advancements. Supervised learning faces challenges like the need for labeled data, which is costly and time-consuming, often requiring expert annotation. Label quality is crucial, as noisy or biased labels can degrade model performance. Additionally, distribution shifts between training and deployment data can lead to performance drops, highlighting the importance of maintaining consistent data environments. Unsupervised learning operates without labeled data, allowing algorithms to discover patterns independently. Unlike supervised learning, it lacks predefined goals, focusing on exploration. This paradigm emphasizes identifying interesting patterns without explicit guidance, offering a mathematical perspective through techniques like clustering, dimensionality reduction, and anomaly detection. These methods enable data simplification, outlier identification, and probability modeling, enhancing understanding of complex datasets. Unsupervised learning encompasses clustering, dimensionality reduction, anomaly detection, density estimation, and association rule learning. Clustering identifies groups based on similarities, while dimensionality reduction simplifies data. Anomaly detection spots outliers, density estimation models data probability, and association rule learning uncovers relationships. These techniques enable data exploration without predefined labels, enhancing understanding and discovery. Clustering in unsupervised learning involves techniques like Gaussian mixture models, which assume data from multiple Gaussian distributions, enabling soft clustering. Applications span biology for cell type identification, image segmentation, and retail customer segmentation. Key algorithms include k-means, hierarchical clustering, and DBSCAN, each offering unique approaches to group discovery. Dimensionality reduction is crucial for handling high-dimensional data like images and gene datasets. Techniques such as principal component analysis, TSNE, and UMAP help visualize data in two-dimensional or three-dimensional, reduce computational costs, and enhance machine learning by removing noise. Autoencoders and variational autoencoders further refine this process, improving performance across various domains. Anomaly detection identifies deviations from normal patterns, focusing on learning typical behavior rather than all anomaly types. It's advantageous when anomalies are rare or unknown, as labeling every type is impractical. Methods include statistical models, which flag low probability outliers, isolation forests isolating rare points, one-class support vector machine defining boundaries, and autoencoders detecting high reconstruction errors. Generative models in unsupervised learning focus on understanding data distributions to create new, similar examples. Unlike discriminative models, which define class boundaries, generative models like generative adversarial networks, variational autoencoders, and diffusion models learn class characteristics. Generative adversarial networks use adversarial training for photorealistic images. Variational autoencoders sample latent spaces for data synthesis, and diffusion models excel in image denoising and creation. And unsupervised learning faces evaluation challenges due to the absence of ground truth labels, often relying on indirect measures and human judgment. Objectives are ambiguous, with multiple valid clustering solutions possible. Scalability is a concern, as algorithms can be computationally expensive, especially with large, high-dimensional datasets. Interpretation is difficult, as discovered patterns may lack human meaning and are sensitive to pre-processing. Supervised learning relies on labeled data for prediction, focusing on minimizing prediction error. In contrast, unsupervised learning seeks patterns in unlabeled data, with objectives varying by application. Supervised methods require costly labeled examples, while unsupervised methods utilize abundant unlabeled data. Evaluation in supervised learning uses metrics like accuracy, whereas unsupervised learning's interpretability depends on context. Supervised learning excels with clear objectives and labeled data, automating tasks like medical diagnosis and translation. Unsupervised learning explores unlabeled data, uncovering hidden patterns, and aiding exploratory analysis. These approaches complement each other, addressing distinct challenges, and can be combined for enhanced solutions, leveraging the strengths of both methodologies. Hybrid learning approaches enhance model performance by integrating various techniques. Semi-supervised learning combines small labeled datasets with large unlabeled ones, ideal for costly labeling tasks like medical image diagnosis. Self-supervised learning generates labels from data itself, useful in tasks like predicting next words. Transfer learning pre-trains on one task, then fine-tunes for another, while active learning selects the most informative examples for labeling. Choosing the right machine learning approach depends on labeled data availability, problem definition, domain expertise, and computational resources. Supervised learning thrives with abundant labels and clear targets, while unsupervised methods explore unknown patterns. Domain expertise enhances supervised tasks, and computational needs vary by algorithm and dataset size. Data quality is paramount. Poor data results in unreliable outcomes. Investing in data cleaning and validation is essential. Feature engineering remains crucial, even with deep learning, as domain knowledge aids in selecting impactful features. Model selection is key, with different algorithms fitting various patterns. Hyperparameter tuning and robust validation strategies ensure optimal algorithm performance. Machine learning represents a paradigm shift, moving from explicit programming to data-driven learning, enabling complex tasks like image recognition. Supervised learning uses labeled data, while unsupervised learning discovers patterns independently. Both are complementary. The field evolves rapidly, with deep learning enhancing performance and blurring learning boundaries. Foundational concepts remain crucial, emphasizing the key insight: learning from data.